So, in this lecture, we'll continue our discussion of experimental tests of symmetries and conservation laws. So, as we said, there are these continuous symmetries and discrete symmetries. And in the last lecture, we discussed the gauge symmetry as well and tests of that. Today, we will discuss these discrete symmetries such as the parity symmetry, time reversal symmetry, charge conjugation, and combined CP and CPT symmetries. So, what is parity? Parity is how a system behaves under reflection of coordinates, where r, the vector r, goes to minus r. So, in quantum mechanics, if you go from r to minus r and then you operate it and you do this operation once again, you have this parity operator operating on it twice. So, the eigenvalue of this p squared operator will be just 1, but then eigenvalue of p is could be plus or minus 1. Okay. So, p squared is 1, but p could be plus or minus 1. So, if you make r go to minus r, then the psi of minus r can be either plus psi of r, in which case we call the parity of that wave function positive, or if it changes sign, then we call its parity negative. When you do this transformation t to minus t in quantum mechanics, you have to also change you have to make the psi its complex conjugate partner. Okay. Then the same Schrodinger equation holds. Similarly, in a charge conjugation, which is often denoted by C, the particle goes to its antiparticle. So, if things are the same with respect to charge conjugation symmetry, then whatever is true for the particle is also true for the antiparticle. I mean, not whatever, the observables that you, let us say, in a reaction or in a decay or something, these rates should be the same. Of course, the charge is opposite. So, if you have a pi plus, then the pi minus has the opposite charge. So, not everything, but some of the processes involved, their rates and decay rates and so on, they should be the same. Now, you can also combine some of these discrete symmetries in the form of CP or all three of them CPT. So, there is a famous theorem called the CPT theorem, which, as far as we know, no process violates. On the other hand, each of these symmetries is violated in some interactions, okay, or in some processes. So, if you want to look, for instance, to parity violation, then you should look for p odd observables, which means that if I make r go to minus r, then if that observable changes sign, then if parity is conserved, then of course you should have a 0 expectation value. If it is violated, on the other hand, then you would see a non-zero value for the p odd observable. So, consider, for instance, a spin of a nucleus and its dot product with the momentum of the electron that comes out in beta decay. This is p odd because sigma goes like r cross p. So, it is p even, but the momentum is p odd. So, overall this quantity is not a scalar, it is called a pseudoscalar, and if this is, for instance, non-zero, then it tells you that parity is not conserved. So, for instance, this will show up as an up-down asymmetry in the angular distribution of beta particles from, say, a polarized cobalt-60 nucleus in beta decay. And this experiment actually we will discuss. This is the famous experiment of Wu. Similarly, you can measure another p odd observable, namely circular polarization of the photon. So, sigma gamma represents the spin of the photon, the direction of the spin, and p its momentum. This is again a p odd quantity, and if parity is conserved, this should be 0. If it is violated, so in case you have, let us say, you measure circular polarization in from gamma rays, which result from the de-excitation following beta emission, beta particle emission, then you will say that parity is not conserved in this process, and indeed such experiments have been done. We will talk about parity violation in beta decay and in weak decays of pions and muons. Okay. So, parity violation in nuclear and particle decays we will discuss. This topic was first brought up by Li and Yang, and the paper reference is given there. They pointed out that there was no evidence that parity was conserved in weak interactions. Certainly, it was conserved in strong interactions, nuclear levels and so on, and the decays they did not violate parity. Similarly, in strong interactions, there was no evidence for parity violation, but in weak interaction, there appeared to be no evidence that parity was conserved. And they were motivated by the so-called tau theta puzzle, which was that it is actually a kaon. The kaon decayed to 3 pions, and since the pion has a spin parity of 0 minus, it's a pseudoscalar. So, obviously, at threshold or at low energies, I mean, when the tau decays, let's say at rest or in its center of mass frame, then the final state has a odd parity, but it is also found to decay into 2 pions, and then they should have positive parity. And these two particles, the tau and theta, they seem to have the same mass and the lifetime. So, they were probably the same particle. Then how is it that the same particle can decay into something which has odd parity sometimes and even parity sometimes? So, motivated by this, they said that it is necessary to look for processes where you can ask the question, is parity conserved or not in weak processes. Now, experimentalists were talking to these two young theoreticians at that time, and they in fact got a Nobel Prize just 1 year after their proposal, because the experiments indeed showed that parity is violated. And so, this is probably one of the quickest events where a Nobel Prize was given uh, within a year or so. So, these three experiments were the experiment, as I already mentioned, that of Wu, where she looked at asymmetries in beta decay from polarized 60 cobalt. Then two experiments which were carried out by Garvin, Lederman, Weinrich, one at Columbia, looking at the muon decay following pion decay, and the experiment of Friedman and Telegdi at Chicago. So, both of these laboratories in Columbia and Chicago had just got accelerators which were above the pion threshold. So, in proton collisions with nuclei, you could produce pions, and then these pions of course decay into muons, and that is what they looked at. The experimental techniques were different, and we will come to that in the following slides. So, the parity violation experiment by Wu was probably the most difficult experiment in terms of putting together many different aspects or systems. So, it used 60 cobalt nucleus, which was polarized in a particular salt, cerium magnesium nitrate, and that is the formula given there. It was cooled to about 10 millikelvin, and with a small holding field, this nucleus could be polarized. Then what is done is that a detector measured at the end of a light pipe, which looked at the scintillation emitted in a anthracene crystal, uh, and using a photomultiplier tube. So, they are counting the beta particles, once with the field or with, let us say, the cobalt 60 polarized in, let us say, the up direction, once in the down direction with respect to the beta particle detector, and they measured this up and down beta counting rate. If you found any asymmetry which corresponded to the observable sigma nucleus dot momentum electron. So, this is as we already saw in the earlier slide, this is a p odd observable. So, if that was found to be non-zero, then it meant that parity was not conserved, it was violated. Similarly, for the angular asymmetry of decay electrons from the stopped muons, the experiment was carried out by these two other groups at an accelerator. So, this is the paper which shows this data. So, this is the setup that was used, and this involved of course making the source It involved putting it in a cryostat with 10 millikelvin. This was done, by the way, you might note, in 57. So, it was quite a challenge in those days. And then to have a detector look at this for asymmetry. Now, what they measured was the count rate as a function of time. So, they cooled it, they measured this asymmetry and then allowed this to warm up. So, then when you warm it up, then of course, the nucleus, the polarization goes in all directions and then you do not get any asymmetry. So, this was gamma ray anisotropy. Okay. Then they looked at gamma ray anisotropy calculated in some way. This is a function of time and it goes to 0 obviously at long times and is finite at early times. So, this is the plot of the gamma ray anisotropy, and this is the beta particle asymmetry. So, you can see here again that this beta asymmetry is measurably non-zero, and then of course, as the temperature increases, then the spin gets averaged out in all directions and then you do not get any beta asymmetry. So, all this data was put together to show that indeed beta decay violated parity, and in fact, when they did this, when they compared it to what you expect, then they found that this is actually violated maximally. And it turns out finally that this is because you have a V minus A interaction and they are of the same order of magnitude. So, obviously, something respects parity, something does not, and so you have a maximal violation of parity in this process. The other two experiments used an accelerator to produce pions. So, this is the so called secondary beam of pions. In this case, it is the 85 MeV beam of pions. I think they used a 400 MeV proton primary beam. This was the experiment done in Colombia, in the basement actually. They had a synchrocyclotron, and this pion beam went through some detectors and ultimately stopped in a stopper. So, within 26 nanoseconds, the pion decays to a muon, and then the muon also stops in this same material, but the decay electron is measured in this detector here. So, these are detector counters which measure the decay electrons. There is also a provision of putting a magnetic field in this. So, there is a coil which gives rise to a small field, and this muon can then precess around this magnetic field. So, what they measured was the as a function of the field current, and the detector is fixed of course. So, you find that the count rate changes in this oscillatory manner. Okay. You can of course in principle do this experiment also in time, and if you have a detector at a fixed angle and you have a fixed magnetic field, in time this count rate will change, and either way you can get the magnetic, you can get a measure of the magnetic moment of the muon, and this is precisely what they did. But more importantly, the fact that you have an asymmetry at all means that parity is violated. So, this was the paper, the title of the observations of the failure of conservation of parity and charge conjugation in meson decays, the magnetic moment of the free muon. Of course, because why charge conjugation? Because of course, pions of both types are produced, and if they cancel each other's effect out, then of course you will not see any effect. So, this also indicated that there is failure of the conservation of parity and charge conjugation. The experiment was done in a different way using a nuclear emulsion by Friedman and Telegdi in Chicago. So, they took pion beams from the synchrocyclotron that was there. These were stopped in photographic emulsions, which is about 1 millimeter thick. It was kept magnetically shielded to avoid a possible depolarization of the decay muons, and they looked at about 1300 pi to mu to electron decays. These were recorded, and they looked at this asymmetry. The W represents the counts that you see from 90 to 180 and subtracted from counts that you see 0 to 90 degrees with respect to the direction of the beam, and divided by the sum total, and you get a angular asymmetry which is roughly 2.5 sigma or so for these events that they saw at that time, 1300 events. Then this sample became larger, and by the time they published, the sample had become about 2000. So, they put it as a footnote, and this asymmetry had grown a little bit, 0.091 plus, I think there is a typo here, this should be 22, 0.022. So, this became about 4 sigma significance. And the inferred angular distribution, so this is just an asymmetry, inferred angular distribution was about 1 plus cosine theta with a prefactor of 0.12. And the fact that this P1 term is not 0 means that, of course, there is a finite asymmetry. And they also mentioned that this A1 is only a lower limit, because of course, the muon gets captured in the atoms of the emulsion, and that contributes to some depolarization as well. Of course, they took care to shield all external magnetic fields so that they do not depolarize, but the muonium, of course, depolarizes it somewhat. So, this is only a lower limit on the asymmetry. The asymmetry is actually larger than this. In any case, A1 not being 0 from the data shows that parity and charge conjugation symmetries are violated, and this is the reference to that paper. Okay. So, now we come to another symmetry. So, of course, as I said, parity violation was discovered. So, people started looking at other symmetries as well, and the time reversal symmetry is another fundamental symmetry. And the way they looked at it is through either through nuclear reaction, where you look at the forward going channel and the backward going channel. So, nitrogen 14 plus a deuteron going to alpha plus carbon 12, but you look also at the reverse channel, carbon 12 plus alpha going to deuteron plus 14 12, and this is the paper. And you plot these two cross sections in the center of mass of the system, and they fall on each other. So, at some level they could put a bound on possible time reversal invariance violating effects. Okay. But the most sensitive test that was proposed in 1950 was that of trying to measure the electric dipole moment of the neutron. The neutron is a neutral hadron, it's a neutral, it's a part of a nucleus, and d goes like E times r integrated over the volume of the neutron. So, since r is odd, then of course, this is also not conserving parity. Okay, maybe I will come back to this slide later. The neutron electric dipole moment, which historically was proposed earlier by Ramsay and Purcell in 1950, they proposed it in the context of looking for possible parity violation. And interestingly, this proposal was made in 1950, and somehow, I mean, this predates the suggestion of Li and Yang as well. But the experiment was carried out later. So, this probably was not referred to in subsequent papers till much later. So, as I said, the fact if the neutron has an electric dipole moment, then of course, this is a signature of parity violation. But since the only vector in the problem is the spin of the neutron, then the dipole moment has to be proportional to the spin. Okay, that is the only vector that you have, and spin is a pseudo vector. Okay, it does not change sign under parity, but it is T odd, because it is like r cross p. So, p is T odd. So, if you find a non-zero value for the electric dipole moment of the neutron, it not only shows that parity is violated, but also that time reversal invariance is violated. Okay. So, the way that people looked for it in later years was that you can make the neutrons, you can first of all polarize the neutron, you can have a spin polarized neutron entering a magnetic field, and then you can analyze the spin of the neutron. And so, in a certain magnetic field, it will rotate by a certain theta, but then you also have an electric field. So, it will also rotate in a combined electric and magnetic field, and the electric field you can switch with respect to the magnetic field. You can have it one way and then the opposite way. So, you are looking for small changes in this Larmor precession frequency. So, you have an interaction which is mu dot B, but plus minus d, where d is the electric dipole moment of the neutron, times a dot product with the electric field. And you can have electric fields of the order of about 20 kilovolt per centimeter, and then you can switch it. So, you can have plus 20 kilovolt per centimeter, minus 20 kilovolt per centimeter, and then you can analyze the spin of this neutron. And indeed, there are even more sensitive ways of doing that. You can have a two-path interference coming about. So, you can look at a oscillation which is you can look at the place where this is changing the fastest and so on. So, there are techniques. I will not go into that, maybe we will come back to that at some later time. But using this, the latest experiments, for instance, have shown, not latest by the way, okay, in 2006, this put a bound on the possible electric dipole moment of the neutron to be about 3 times 10 to the minus 26 e centimeter. Now, this is an extremely tiny quantity. Maybe you can take it as an exercise to show that if the positive and negative charges are, if the neutron is blown up to the size of the earth, how much would be the displacement between the positive centroid of the positive and negative charges. It will turn out to be very small, surprisingly small distance. But at this point, I will just say that we have only found an upper bound, and people are still pushing for better and better, more sensitive experiments to push this number to 10 to the minus 28 e centimeter. And there are several of these projects going on in Institut L'Avellangevin in France, at the PSI in Switzerland, and at the Oak Ridge National Lab in the US. So, the history of the electric dipole moment measurements of or bounds on the possible electric dipole moment of the neutron, they are given here. The early ones gave a bound of 10 to the minus 19 ECM, and over the year, this is taken actually from a review article, I think of Ramsey probably, where the bound has improved by about a millionfold. Okay. So, that was the bound in about 2006, and of course, there are present day experiments which have taken this down further by another factor of 5 to 10. And there are some predictions of supersymmetry which are in this band, and standard model predictions of course give a much lower value. However, it will take I think several probably decades to reach that bound, if at all. Now, let us talk about another symmetry called the CP symmetry. So, we know that parity is violated in weak decays such as pion going to mu plus and nu mu, but Landau proposed that if you change the particle to an antiparticle, that means you take the charge conjugate partner, then Cp might be still conserved. So, from here you change particles to antiparticles, which means pi plus goes to pi minus and mu minus goes to the anti-muon type of neutrino, then is this process happening? And indeed, this process did seem to be happening. So, does happen in fact. So, where the directions of the momenta are reverse, but not those of spin, because of course parity does not change the sign of the spin, but the anti-neutrino now is right-handed. So, this process goes through. So, CP symmetry is conserved in weak decays and weak processes such as this. But it was found that CP is not a good symmetry in the case of K0 anti-K0 oscillations or B0 anti-B0 processes. For instance, if you take the K0 and anti-K0 and combine it in a certain way, you get the K long, which is a CP minus 1 eigenstate. These decays violate CP since they normally decay through 3 pions, but small fraction of the time they decay about 1 per mil into 2 pi's, and that is Cp plus 1. So, you have violated this process, and this violation of Cp was discovered by Christensen and so on, for which Cronin got the Nobel Prize at a later time. This is found in 64, and much later the B quark was discovered, and then the B mesons were discovered. So, this process also occurs in the B0 anti-B0 systems, and this in fact has been is investigated very deeply, very minutely in E plus E minus colliders such as at SLAC and KEK. Now, if this Cp is violated, then it also leads to a consequence that it implies that there is an asymmetry between matter and antimatter. And we know, for instance, that our universe consists of matter, and we don't have evidence of antimatter in even the farthest galaxies that we have seen. So, why is there a preponderance of matter over antimatter? Is this violation enough to do that? So, if you have a 1 in 10 to the 8, 10 to the 9 violation of CP, then you can explain the present day matter dominance. However, this particular decay that is seen is not enough to explain this asymmetry, and we have to look for other places, including in the leptonic sector. For instance, is there CP violation in the neutrino sector? And if that is large enough, if that is found to be there and large enough, then maybe through processes that violate lepton and baryon number, you can get this asymmetry between matter and antimatter. Okay. Finally, we come to this combined symmetry, which is the CP symmetry, and if this CPT symmetry holds, then the mass of the proton and antiproton should be the same, and this in fact has been measured. There is a typo here. This should actually be MP antiproton. So, this is been seen that this, if at all there is a small difference, it is less than 1 part per billion, and this has been done by using 2 photon laser spectroscopy in antiprotonic helium. So, you actually create antiprotons, slow them down, get them captured on helium in helium, and this is the so called Asakusa. And then the antiproton, of course, it has a negative charge, so it goes deep into the helium atom with a size which is about 2000 times smaller than that of the electronic orbit, and that way you can measure this antiprotonic helium to give you the, so you measure a transition in the antiprotonic helium, and thereby, since that transition energy depends on the antiproton mass, you can get a bound on the difference between these two masses. So, the earlier result of M. Hori and so on was that E by M for a proton and E by M for an antiproton using free particles, that was of the order of 10 to the minus 10. But this used a different way of attacking the problem, and there is another way you can look at the difference, a possible CPT violation in K0, K0 bar masses, and they are found to be equal to within 10 to the minus 19 or so GeV. So, this bound is also sort of probably better than the bound that you get here, or these are of course different numbers, this is a ratio, whereas this is a actual absolute mass difference. So, anyway, so these are the bounds that exist in literature. So, we yet haven't found evidence for CPT violation, and of course, theory tells you that CPT should be conserved, and there is a fundamental theorem due to Pauli which says that CPT should be conserved. Finally, I talk about isospin symmetry. This is the symmetry between neutrons and protons. They have very similar masses. So, this was proposed by Heisenberg a long time ago in the 30s, mid 30s. So, you can assign a isospin of half to neutrons and protons, and the Z projection tells you whether it is a proton or a neutron. So, depending on whether you are doing particle physics or nuclear physics, the isospin is plus half for a neutron if you are a nuclear physicist, and minus half for a proton. So, the isospin Tz for a nucleus is half of n minus z, where n is the neutron number, z is the proton number. Similarly, you can assign isospin to the pions, and since there is a triplet, you have to give a isospin quantum number of 1, and Tz equal to plus 1 for let us say the pi plus, Tz equal to minus 1 for pi minus. As I said, this convention is what I am saying is the convention used by nuclear physicists. Particle physicists use the opposite convention, where they put a minus half for the proton and plus half for the neutron. The Coulomb interaction breaks this isospin symmetry, because of course protons have charge, whereas neutron does not have electric charge. However, because the nuclear forces are much larger than Coulomb energies, in light nuclei, the states in boron 12 and carbon 12 can be sort of mapped onto each other apart from the DC shift. So, the so-called T equal to 1, so you can see that boron 12 has a isospin of 1, whereas carbon 12 has equal number of protons and neutrons. So, this is a T equal to 1, T equal to 0 state, but there can be excited states of T equal to 1, and this would be the so-called isobaric analog state of boron 12 in carbon 12. This happens to be at 15.1 MeV, and these three states, boron 12 ground state, the T equal to 1 state in carbon 12 at 15.1 MeV, and the nitrogen 12, which is also a T equal to 1, they form an isobaric triplet. And the difference in energy is just due to the Coulomb interaction. So, if T is conserved, then in any nuclear process, the initial isospin should be equal to the final isospin. So, for instance, the 15.1 MeV is a sharp state because it is T equal to 1 and it would be decaying to T equal to 0 states, namely this carbon 12 excited state, since it is above the alpha threshold of 7.3. So, it is almost like 8 MeV above that threshold. So, it can decay into alpha plus beryllium 8, but the beryllium 8 has T equal to 0 and alpha also has T equal to 0. So, this process would then violate isospin. Of course, it also violates angular momentum because this is it happens to be J pi equal to 1 plus state, and the beryllium 8 and alpha have spin zeros. So, you require to do something about that, and you have to have a L equal to 1 coming in, so that you get the angular momentum right, but then you have to also conserve parity and so on. So that's why this state is actually a sharp state. It decays mainly by photons to the lower states in carbon 12, and so the gamma decay is actually 90% of the branch, whereas you would have expected from that if you didn't look at some of these aspects, you would have expected that this state should have widths of the order of MeVs. In fact, it has width of the order of electron volts. Okay. So, in summary, I should say that we looked at experimental tests of parity conservation, and of course, that they were violated, parity was violated in beta decays. We looked at measurements related to time reversal invariance by looking at T odd observables, including the neutron electric dipole moment. Oh, there is something that I forgot. I should go back in slides. There is another very nice way of looking at time reversal invariance and its possible violation, and this is the decay rates of K0 and K0 bar. So, the rate of K0 bar going to K0 is not the same as K0 going to K0 bar. So, the reverse decay rate is different, and the measured asymmetry in these decay rates is of the order of 6 point, so a few times, let us say 7 times 10 to the minus 3. So, it is in parts per mil. However, and this is the paper. This experiment was done in C.P. Lear in CERN. These are the two papers that talk about this measurement. This is a direct evidence for T reversal invariance violation. But there was another measurement carried out by the KTEV collaboration in Fermilab, which looked at the asymmetry in the K long decay into pi plus pi minus and E plus E minus. Now, if you look at the angular asymmetry, then this is like looking for a T reversal invariance violation. And in fact, they found that there is a large T violation of the order of about 13% or so, and this is well beyond about 5 sigma level. So, if there are no other systematic errors, then this is a case where you have found a large T invariance violation, and this is the paper in 2000. Okay. So, I am sorry that I came back after coming to the summary slide, but in any case, this is an exciting area where direct time reversal invariance violation has been seen. So, coming to the summary slide, we have seen evidences of putting bounds on the neutron electric dipole moment, but also finite value for T odd observable in kaon decay and kaon K0 to K0 bar and vice versa. Finally, we also had mentioned isospin symmetry and how it operates in hadronic nuclei. I did not talk about the delta resonance, which has 4 states. So, it is a T equal to 3/2 entity. You get the doubly positive charge, singly positive charge, neutral delta and the negative delta. So, there is a symmetry there as well. Okay. So, I come to the end of this lecture. Thank you.